All right, so just to show you this, just to go through these notes quickly, rational function with oblique asymptotes. So remember, rational function is one thing divided by another function. And you can recognize that there's going to be an oblique asymptote if the degree of the top minus the degree of the bottom is equal to 1. Then you're going to have an oblique asymptote. We'll explain through the explanation just now. So if the limit to infinity is a constant, so if the limit, remember, as x tends to infinity of some rational function f of x is equal to k, then y is equal to k would be the horizontal asymptote. Okay. Now what's going to happen is we're going to find the limit as x tends to infinity, and we're going to get an answer not of y is equal to k. You're going to get the limit as x tends to infinity of f of x is going to be something of the form mx plus c, and that's going to be an oblique asymptote. Okay, so because they're both limits to infinity, you can't have a limit which is a constant and something of the form mx plus c. Okay. So to find the equation of the oblique asymptote, we simply divide the numerator by the denominator, and the quotient, in other words, the answer we get, will be the equation of the oblique asymptote. So it says for each function below, determine the equation of the asymptotes. Well, first of all, probably easiest to just look at the vertical asymptotes first. Okay, so we've got 3x cubed, this function over here, 3x cubed over x squared minus 16 simplifies to 3x cubed over x minus 4x plus 4. Nothing is going to cancel. If they cancel, it would be a removable discontinuity. So there are two values that x can't be. X doesn't exist, the function doesn't exist at 4 and at -4. So those are your vertical asymptotes. X is equal to 4 and x is equal to -4. Okay. Then the degree of this is 1 more than that. So we're going to have an oblique asymptote. So to find the equation of the oblique asymptote, we're going to divide 3x cubed by x squared minus 16. The way I do it is at force and balance method. So I force x squared minus 16 into the numerator, but then you've got to balance it. So you've got 3x cubed, which you had, but now you've got minus 48x, which wasn't there before. So to balance it, you've got to add 48x. Okay. Then that divided by that will just leave you with 3x, but you've still got 48x over x squared minus 16. As soon as the degree is of the numerator is less, not less than or equal to less than the degree of the denominator, then you can't divide anymore. So that's the furthest we can go with the division. Okay. So your oblique asymptote is always going to be simply be the quotient. Okay. In other words, the answer that you get after you've divided out. So in this case, your oblique asymptote is the quotient, which is, there's your quotient, 3x. So your oblique asymptote is going to be the line, y is equal to 3x. Now, that's all you'd have to show, the working you'd have to do in order to do that. But this is just an explanation. As it says over here, you don't have to show this, you have to write that down ever. Okay. So remember, oblique and horizontal asymptotes have to do with limits to infinity. So if I took the limit to infinity of this 3x plus 48x over x squared minus 16, okay, you're going to get the limit as x tends to infinity of, you can split up the limits, do them separately, of 3x plus the limit as x tends to infinity of 48x over x squared minus infinity. As x tends to infinity of 3, so if x was a million, in this bit over here, y would be 3 times a million. So it's getting infinitely close to 3x. Over here, though, the limit, if I find the limit as x tends to infinity of this, I take out the normal method to find a limit to infinity. I take out x squared, and I'm left with 48 over x. Take out x squared from the bottom. 1 minus the x squareds cancel. Okay. And if I put in a massive number, that thing over there would become 0, and that becomes 0. So I'm left with 0 over 1. So I get 3x plus 0, which is just 3x, which is why, as x tends to infinity, y tends to 3x. So the oblique asymptote, as the x values get bigger, the y values get closer and closer to the line, y is equal to 3x. So we said that y equal to 3x is the oblique asymptote. Okay. Remember, the degrees of the numerator and the denominator are the same, or the degree of the numerator is less than the degree of the denominator. Okay, then you're going to have a horizontal asymptote. So here, in this one over here, the division's been done for you already. Okay. So your vertical asymptote, once again, what can't x be? X can't be equal to 1. The oblique asymptote is the quotient. So as you can see over here, the quotient is the line y is equal to 4x. Okay. Again, if you want an explanation, and you don't have to do this, you find the limit to x tends to infinity of the whole thing. The limit at x tends to infinity of 4x stays as 4x. This thing over here, you're going to have 3 over x squared minus 2x plus 1 if you times that out. And if you go take out x squared as the biggest power, you get x squared over 3x squared at the top and x squared over 1 minus 2x plus 1 over x squared at the bottom. The x squareds cancel, and you'll end up with 0 over 1. So it's 4x. So as x tends to infinity, the y values get closer and closer to the line, 4x. Okay, this one over here, example 7. Okay, and this is a typical kind of question. Given g of x is equal to x squared minus 2x plus 1 over x plus 1. First of all, if you're going to sketch this graph, you'd have to find the intercepts. So if I put x is equal to 0, y is equal to 1, okay, and likewise, if I put y is equal to 0, well, the whole thing can only be 0 when it's where the numerator is 0. Okay, because if the denominator is 0, it's undefined. That's why it's important to make a note that x cannot be -1. Okay, that's your restriction. It's really a good habit to get into writing that down all the time. So I get x 0 is equal to x squared minus 2x plus 1, which factorizes to x minus 1 squared. So when y is 0, x is equal to 1. Okay. Then determine the equation of any asymptotes that exist. Well, once again, if I factorize the numerator, x squared minus 2x plus 1, okay, that factorizes to x minus 1, x minus 1. Nothing cancels, so there'll be no removable discontinuities, but there will be a vertical asymptote at x is equal to -1. The degree of the numerator is 1 more than the degree of the numerator. So the degree of the numerator is 1 more than the degree of the denominator. So there's going to be immediately we know there's going to be a oblique asymptote. As I said, if they were the same, or if the degree of the numerator was less than the degree of the denominator, it would be a horizontal asymptote. So we do that force and balance method of division. Okay, so I force x plus 1 into the numerator. Got a balance to times back out to get x squared minus 2x plus 1. So at the moment, you've got x squared plus x, but it's got to be minus 2x. So what do you have to do to get to minus 2x? You have to minus 3x. That's the balancing bit. And we've still got that one that we initially had in the question. So it balances out and becomes x back to x squared minus 2x plus 1. Here, the x plus 1s will cancel. So we're left with that x. Okay. Then I've got minus 3x plus 1. Okay. Now I've got to balance again. So now I've got to work with the 3x plus 1. So I force the 3 in. Okay. When I force the 3 in, I'm going to get minus 3x minus 3, but it should be plus 1, not minus 3. So what do you have to do to minus 3 to get to plus 1? You have to add 4. Now that'll divide out, and you're going to get x minus 3 as your quotient plus 4 over x plus 1. This is now less. The degree, as soon as the degree of the numerator is less than the degree of the denominator, then you have to stop dividing. So the oblique asymptote is the line over here, y is equal to x minus 3. Okay. So oblique asymptote, y is equal to x minus 3. It's a quotient that you get after you've done your division. Okay. Nearly done. Okay. Now find the coordinates of the stationary points that exist. I'm going to show you 2 ways. The one is to work with the original equation. So when does the stationary point happen? Stationary point happens when the gradient is equal to 0. What gives you the gradient? The derivative. So if I use the quotient rule, the derivative of the top, x squared minus 2x plus 1 is 2x minus 2 times the bottom, which is x plus 1, minus the derivative of the bottom, which is 1, times the top, which is x squared minus 2x plus 1, over the bottom squared. You go simplify. This whole thing will be equal to 0 when the numerator is equal to 0. Okay, so we should put x can't be -1 as soon as I get rid of the denominator. Okay, and I solve for where the numerator is equal to 0. The numerator simplifies to x squared plus 2x minus 3 is equal to 0. So the gradients are going to be 0 when x is -3 or x is 1. The alternative method, which I generally prefer, in the previous page, we worked out that after division, this whole thing, g of x, became x minus 3 plus 4 over x plus 1. So you could work with a simplified form if you wanted to. Either way is equally correct. So if I use g of x is equal to x minus 3 plus 4 over x plus 1, and I solve for where is g dashed x is equal to 0, well, the derivative of x is 1, derivative of -3 is 0, so that disappears. So then I basically find the derivative of 4 over x plus 1. I could use a quotient rule and say the derivative of, basically I've got 0 over here, because the derivative of the top is 0. Okay. Then minus the derivative of the bottom is 1 times the top, which is 4 over x plus 1 squared. You're going to times everything out by x plus 1 squared. Minus 4 is equal to 0, and you get back to x squared plus 2x minus 3 is 0. So either way, you get x coordinates of your stationary points at -3 and at 1. If I now sub x is equal to -3 back into either one of this, I could either use that form or that form. Put -3 back in, replace every x with -3. So you get -3 minus 3 plus 4 over x plus 1. We end up with when x is -3, y is -8. And likewise, when x is equal to 1, y is equal to 0. So your stationary points are at 1, 0, and at -3, -8. Now, you're then asked to draw this thing. Okay, when you're asked to draw it, after all this work you've done, I did a little summary. So our summary is that our stationary points are at -3, -8, and at 1, 0. Our intercept was at 0, 1, and 1, 0. The vertical asymptote we worked out was x is -1, and the oblique asymptote was y is equal to x minus 3. When you're drawing a straight line, the easiest way to do it is find the two intercepts. So in this, when x is 0, y is -3, and when y is 0, x is equal to 3. So those are the 2 points you're going to need for your oblique asymptote. So if I draw in the oblique asymptote, it goes through 3, 0, and 0, -3. I draw in the oblique asymptote. Label those 2 points, please, the intercepts of the oblique asymptote. If I draw in my vertical asymptote, it's x is equal to -1. Then with stationary points, I actually write SP on the graph. So the stationary point is 1, 0. This is to remind me that the graph turns at that point. Likewise, the other stationary point is -3, -8. Okay, so now I've got my stationary points and I've got my y-intercept, which is at 0, 1. So remember, a graph can never, ever cut a vertical asymptote. So it tends towards the vertical asymptote. It must go through that point 1, must turn at the stationary point, and then it's going to head off. As x tends to infinity, y values tend to the line. We should label this y is equal to x minus 3. This was the graph of g of x. So as x tends to infinity, y tends to the line x minus 3. Okay, over here, my stationary point was at -3, -8. Okay, it's a function, so you can never have y values in the same area. Okay, so it must, as x tends to negative infinity, once again, y tends to this line x minus 3. It turns there, and it must head towards your vertical asymptote, which it